Good morning, everyone. Welcome to the first press conference today, the third of the General Assembly. The press conference is on the changing Arctic, and I would like to remind the floor that we'll open for questions following short presentations by the speakers. And people watching us remotely can also ask questions on Twitter by using the hashtag AskEGU or on Skype by adding EGU.media to their contacts. Any documents relating to this and other press conferences are available online on media.egu.eu/documents. Taking part in this press conference, we have Juliana Panieri, an associated professor in environment and climate at the Arctic University of Norway. Jean-Claude Goscard, who is an oceanographer emeritus at the CNRS, the French National Center for Scientific Research, and is based at the Pierre and Marie Curie University in Paris. And Hayu Aiken, who is a professor at the Geophysical Institute and Department of Geology and Geophysics at the University of Alaska Fairbanks in the US. And I'll hand over to Juliana.
Good morning. So you might be interested to know that in the Arctic Ocean marine sediments, there is a vast amount of methane as a free gas and in the form of gas hydrate. The gas hydrate is a solid compound formed when the methane and water combine at low temperature and moderate pressure. So nominally, in 1 cubic meter of gas hydrate, there is 164 cubic meters of methane. So warming a small amount of gas hydrate could significantly contribute to global warming, and then this amount of methane can affect the global warming. Okay, so in the Arctic marine sediments, as I said, there is a vast amount of gas hydrate, and the main goal we have at the Center of Excellence for Arctic Gas Hydrate that has been recently established at the Arctic University of Norway is to understand if there are any relationship between the methane emissions from gas hydrate melting and the global warming. To do so, we concentrate our investigation on several areas in the Arctic Ocean, and at the same time we are establishing an innovative technology and an innovative way to do research. So we use a research vessel, we use ocean observatories, and we use methane sensors to study the methane emissions. So we would like to quantify how much methane there is in the marine sediments, how much methane escape from the ocean floor, and how much methane reach the atmosphere. So at the same time, we study long records of marine sediments, which represent an archive of data and these data are extremely useful to reconstruct the evolution of the environment through time. So there is a proxy, there is a tool which is proven to be extremely useful and reliable to study the methane emission in the past. And this tool is a group of marine organisms, which is called the foraminifera. So here you see a couple of examples. These are 3D models to show you how they look like. And you see here, they are really very nice. But in these glass vials, you see how they really are. They are tiny, tiny marine organisms. They live in all oceans from shallow to deep water. And they have a shell to protect themselves. This shell is of calcium carbonate. And when they make their shell, they use the carbon from the ocean water. And they use both of the isotopes of the carbon-13 and the carbon-12. So measuring the ratio between carbon-13 and carbon-12, they can provide the data to reconstruct the carbon cycle, the global carbon cycle. But when there is methane in the system, so this ratio is extremely affected and become extremely negative. So we see deviations from the baseline. Okay, and this is a clear indication of methane emission in the system. Okay, and the data we have obtained so far, measuring these isotopes in the forams from several areas in the Arctic, reveal that the methane emissions in some areas in the Arctic Ocean have occurred over the past 16,000 years ago, at least, with some interruptions. So we are going to expand this time scale. This is something that I can already tell you. And the methane emissions show that there is an apparent correlation with the warmings. And the first warming, it's at the end of the last glacial period, between 4,700 and 12,700 years before present. And the second warming, it's at the beginning of the last interglacial period, around 11,700 years ago. We see different amplitudes in the ratio obtained measuring the forams, and we think that these different amplitudes are due to different amount of methane in the system. And at the moment we are working to prove these hypotheses. So I would like to conclude telling that we will make predictions for future. However, there are many uncertainties related to the fact that the Arctic is difficult to assess. But the team at the Center of Excellence is using a frozen-in research vessel to detect how the methane emissions from gas hydrate melting change through short time interval. And so using the different amplitudes that we obtained measuring the ratio in the forams, at the same time using the data from present-day methane release measurement from the ocean floor through the column water into the atmosphere, will give us the possibility to have data that we can use to model the methane emissions from gas hydrate melting in the future in the Arctic.
Good morning. So I have a presentation here. I extracted half of the slides I presented this morning to a session on ocean science for polar oceans, since I have a half time that I had this morning. So I want to go quickly through all of them. There is no projection on the screen. Okay. This is just an overview of the situations for the Arctic sea ice over the past 30 years. It's back to when we started the observation with satellites, roughly. And you see, this is a picture from an instruments called the Advanced Microwave Scanning Radiometers, which is a very precise instrument that is giving us the ice concentrations in the Arctic every day, days and night, and with clouds or no clouds, because it's microwave frequencies that we use the emission from the Earth, and that's very precise information about sea ice. We see the evolution of the sea ice extent from the period 79-83, which is in orange, which was covering something like more than 7 million square kilometers of the Arctic, which represent about half of what is produced in winter, or was produced in winter, because now the situation is quite different, especially in 2007. We see this is the cyan color, which indicates a strong retreat of sea ice. This record in 2007 has been even more rich during the 2012 event, which is not on these presentations. So all the information we have are more or less collected on these slides, on the red curves, plus the stars in 2007, 2012, from which, if you extrapolate, give you the indication of disappearance of sea ice in the Arctic in summertime by the mid-20s or early 30s. Compared to the IPCC projections in blue, which are lagging quite a bit, but this is now under revisions, and the modeling predictions are better than that. But still, we have a lag between observation and models. What is even maybe more important than the sea ice extent, which is quite visible from satellite, is the volume. Sea ice has a certain thickness that we need to take into account. It's not much. It varies from 2 to 3 meters on the average. Of course, you have ice ridge, which are much thicker than that, or you can even have leads with no ice in between ice flows. But on the average, this is produced by a model used by the University of Washington in USA, the biomass model or project, and from which Overlang and Wang in 2013 were able to calculate the sea ice volume loss at the end of the summer over the past 30 years. So you see there is a 75% ice mass loss over this period, which include a 50% sea ice extent retreat or reductions, combined with a 50% reduction in sea ice thickness. That give you a 75 loss in the volume or mass of ice. We have been investigating the strength of the winter, because before melting ice, you need to form ice. So it's important to look at the conditions in winter when you are producing the sea ice. And we are using the ERA interim data reanalysis over the past 30 years, and it's the most accurate information we have over this period of time. We were able to calculate a very simple parameter, which is the freezing degrees days. It's, for instance, if you have minus 20 degrees below freezing for 100 days, it's produced at 2,000 freezing degrees days, and that corresponds to about 1 meter of ice. So we calculated this parameter for this all this time period, and it's obvious. Be careful on these maps. The red colors are the cold, up to 7,000 or 8,000 freezing degrees days accumulated over the winter period. But you see that for more recent years, in lower right of the graph, the color is much pale, much more pale than before, and it corresponds to a loss of freezing degrees days of about 2,000 freezing degrees days over the winters. So winters in the Arctic are milder and producing less ice. This is logical. And less ice means a good 1 meter of ice less than before. From these, you can directly calculate this ice volume formed in winter. And that's the result from the previous freezing degrees days I showed. And going from 28,000 cubic kilometers in cold winters in the late 80s, early 90s, to almost 20,000 cubic kilometers now. So there is a loss that you can compare with these estimations, which is at the end of the summer. This other one is at the end of the winter. It's the ice you formed in winter. This is the ice you melt at the end of the summer. But you see that the two curves are pretty much parallel. So the ice missing in summer has been already missing in the winter period before. Last we did, and I will conclude on that, is to look at this ring, which we call the seasonal sea ice zone, where we have the most drastic evolution of sea ice extending from 70 north to 80 north which is about north of Spitsbergen, Greenland, the Canadian archipelago, and Svernaja Zemlya. So we look at this area, this ring, 70, 80 north, over the same time period. And this is what the results are. So you see two things important there, or even three. One is the deepening of the trough, which is the September minimum. So you see that in this area, in this ring, in 2012, which is the black curve, we almost had no ice in this entire ring around the Arctic. It was entirely a seasonal sea ice zone at that time. But the other important elements there is that you see from year to year over the last 10 years, there is an advance of the breakup, which is when the ice is decreasing from 6 million square kilometers to 1 million or less in this ring. You see that this is occurring earlier and earlier every year, minus the interannual variability, which may create some noise on that. But this advance in the breakup season is something of the order of a month over the last 10 years, so it's changing pretty rapidly. And the third element is on the other part of the curve when you are forming ice again. So this is the freeze-up, which is delayed by nearly the same amount. So this is characteristic of the opening of the Arctic, which, to my opinion, is more important than knowing about the year where any particular day in September will be an Arctic Ocean free of ice. This advance in breakup and the delay in freeze-up is a really important things. My conclusions are on this last graph. I just would like to stress your attention on the bottom lines, which indicates that what I just said about this importance of looking at this breakup season, which starts earlier and earlier every year over the past 10 or 20 years, and the delayed we had in the freeze-up during late fall. And this is very important for marine and also terrestrial ecosystem in the peri-Arctic regions, as well as for human activities, socio-economic importance of these, and climate and weather for the northern hemisphere. Thank you.
So at the University of Alaska in Fairbanks, we're looking at the impacts or implications of Arctic sea ice change, and one of the things that we're investigating in more detail as part of a Center of Excellence for Maritime and Extreme Environment Security is how these changes in ice cover actually impact things on the ground. As I'm looking at this here, I'm actually seeing that there's a slight issue with the presentation. So I'll show these slides in a large screen mode here, but this is part of a presentation that I'll be giving tomorrow morning in a session on cryospheric hazards. So I invite you to have a look at that in more detail on the EGU website as well. The key issue about sea ice hazards that we're finding is, which makes it such a complicated topic to address, is the fact that ice hazards, which imply damage or threats to human activities, are very closely intertwined with ice uses. And so what we're seeing is, and Jean-Claude was alluding to that, is that these changes in the ice cover that create open water areas in the summertime at the same time are also being used and exploited by various parts of industry. So you see a significant increase in oil and gas exploration in the Arctic. But during that time period, you may still have a very significant probability of encountering ice. And evaluating the combination of potential impacts or exposure of infrastructure, whether it's vessels, whether it is coastal communities, linking that to the potential damage and potentially disastrous outcomes. That's one of the big challenges that we're trying to address now. So what we've done is look at this in terms of, and this is briefly illustrated on the slide here, is look at this in terms of so-called slow onset hazards. And those would be processes that actually take years or decades to unfold, or in the case of methane emissions, potentially centuries. And then we have these so-called rapid onset hazards, where literally you see this in the illustration here at the bottom right. If you have structures in the ice, such as oil production platforms or vessels, where ice impacts, that occurs on very short time scales, very localized. And what we're finding is, in some of this work, which involves government agencies, different stakeholders, is that as you may be aware, if you have a rapid onset disaster, typically response is effective, very quick. Slow onset hazards are much more difficult to deal with because they're more difficult to project. That's one of the key challenges. And a lot of the government agencies that are set up to deal with specific short-term disasters are not necessarily well equipped to deal with slow onset hazards. So that has been one of the focuses of our work. And just as an illustration here, I'm showing you a slide that you've already seen earlier. This is the area of the Arctic ice cover where we've seen the largest reductions here in the North American and Far Eastern Russian Arctic and summer ice extent. And these changes in ice cover have, as an example from the perspective of slow onset hazards, two very important consequences. The first is that the ice cover actually performs an important service for coastal communities insofar as it helps keep down wave action. It keeps the ocean in front of the coasts cold. And with the lack of ice that we're seeing in recent summers, we're starting to see significant increases in the rates of coastal erosion, both because there's more heat, as Jean-Claude already alluded to, transported to the coastline. So permafrost in the coastal areas starts to thaw more rapidly, and at the same time, fall storms present a direct threat to the coastline. However, at the same time, even in the presence of sea ice, we're finding that ice is a very effective geologic agent in its own right, and the role that the ice cover plays in moving sediments over large scales, over long distances in the Arctic is currently not well understood. What we're seeing is, from some of the work that we've conducted, is that there's an increase in the amount of sediment transported by ice. And that has a number of different consequences, including potential transport of contaminants. So putting this together, one of the things that we've now examined is, and I'm showing you a map here of the Arctic Ocean where, the key detail is you see a lot of different colors. These represent areas of significant human activity. And of course, human activity goes along with exposure of infrastructure to environmental hazards and hence potential risk. What we've been looking at is to find better measures to describe this type of risk in terms of where do we see activities, and of course these activities are increasing significantly in recent years, and where are those activities exposed to, in particular, sea ice hazards. So some of the work that we've been doing that I'll talk about in more detail tomorrow has looked in this context at rapid onset hazards, this question of, for example, the areas north of Alaska and northern Canada currently are experiencing significant activities from the perspective of oil and gas exploration. Quite a bit of activities in the summertime. Some of this has been gone through or has been discussed in the media. And in that context, we're finding that because of increased year-to-year variability, those activities are still, even with a reduced ice cover, exposed to significant ice action. One example to do that is, and again, this is a summer slide that you have access to through the EGU press website. We've done a fairly exhaustive review of the different types of ice properties that are relevant from a risk perspective or a hazard perspective, and this is working with ice users, different stakeholders, and then rely on existing satellite remote sensing data. Some of this has already been shown earlier. Here's an example that highlights areas of significant ice deformation, and ice deformation is a substantial hazard because it creates both very thick ice and it represents a challenge to shipping during the ice shipping season. And as we do this, we're finding, and that's illustrated in this slide here, we're finding that despite reductions in ice extent over these areas in the summertime, a change in ice movement and ice deformation that has gone along with that change, we're still seeing substantial production of hazardous ice, such as these large so-called flowbergs. These are thick blocks of sea ice that ground in shallow water, 25 meters, 30 meters water depth, can be as much as 30 to 40 meters thick. And these types of regionally produced flowbergs represent a significant hazard, in particular because they're upstream of some of the major oil and gas exploration areas. But again, the other aspect to the problem is that this type of ice is also very important as a means of stabilizing the coastal ice cover. So on the one hand, industry has to consider potential threats by this type of ice. On the other hand, in some of the coastal regions here, the very same types of ice features help ground shore-fast ice and actually enhance the use of the coastal sea ice. And of course, these types of ice are also very relevant because they have a habitat value to different organisms and are being used by coastal communities in this area here, the Inupiat, who are the indigenous peoples living in northern Alaska. So in conclusion then, what are the key points? One of the key conclusions from our work, and again, this is something I'll discuss in more detail tomorrow, is that we're seeing a convergence of both increased activities and significant changes in the ice cover along the coastal regions. So if you look at these maps, and I'll show more of those tomorrow, you find that those areas where we find highest hazards are also areas where we see highest levels of human activity. At the same time, we're also seeing potentially increasing overlap of uses of ice-covered areas, and that, of course, has a potential for conflict between different users and, again, key element in the perspective of ice hazards. And one of the things that we're working on now is to establish or derive better measures of the extent of hazards posed by sea ice and what that means in terms of risk evaluation. Thanks.
Thank you very much for your presentations. We'll now open the floor for questions. Does anyone have any questions? I think there was...
Jonathan Amos, BBC. Jean-Claude, can you just expand a little bit on why you think the early breakup and the late freeze-up are as important an issue as the minimum itself? You just mentioned this at the end. You emphasised this at the end. Why that emphasis?
Yes, there are several. First of all, I want to relate my presentation with what Ayo mentioned about sea ice hazards. When, as a climatologist, I say there is no ice in this ring, this is not exactly true. If you look at ice flows or piece of ice, we can also add to the sea ice hazards, icebergs, growlers, and bergy bits, which are more and more important with all these ice melting away. So the hazards by sea ice and icebergs are very important in the actual situations. To answer your questions, I think the advance in breakup and the delay in freeze-up in the fall is important because this is the variable which is going to change after we reach the point where we have a number of days in the September, in the end of the summer, where the sea ice, the Arctic is free of ice. I mean, that will be not the point anymore. The point will be when the breakup starts and when the freeze-up starts. And this has several implications for marine ecosystems. I mean, polar bear, for instance, we have discussed that at length before. But this population of of polar bears are very sensitive to this break-up timing, as well as a freeze-up because of the feeding habits of these animals. And but it's also important for human activities if we know that the sea ice will form again in winter. There is no doubt about that, at least for certain times. So it's important for navigations along the Northern Sea routes to know when the breakup starts. This is important for navigations, for oil and gas exploitation. It may has also some importance on the marine ecosystem because all these marine mammals and living organisms in the oceans are really dependent on this sea ice evolution. So I think this sea, and also because we see an evolution, constant trend in the start of the breakup in the spring, earlier and earlier, and the delay in the fall. This is something we were not really could expect initially. In addition to this sea ice September minimum, which is attracting most of the interest of the media in September. So again, in September, we may have also an extended period of time during which the Arctic Ocean will be sea ice free from a climatologist point of view, as I just mentioned. But again, it's very important to see this breakup timing and freeze-up timing and how it evolves in the future. The model predictions are also we are looking at the model predictions for these particular aspect, which it's a very sensitive issue.
Thank you. Are there any other questions?
I'm Julia Rosen. I'm working for EGU. I'm a freelance science writer. I have a question for Juliana. How do you reconcile your results with ice core records of methane isotopes, which don't seem to suggest a strong role for clathrates? Is it possible that the methane may not have crossed the air-sea interface?
Yeah, I mean, what I can say is that when you have gas hydrate melting, you have emission of methane. The methane escapes from the ocean floor and then goes to the column water and then to the atmosphere. But we have to say that it's a small amount of methane that reach the atmosphere, because most of the methane is consumed by bacteria at the ocean floor, and then another part of the methane is consumed and dissolved in the column water. So it's a very small amount of methane that reach the atmosphere. But there is some methane that reach the atmosphere. And then we know that the methane is a greenhouse gas, which is 20 times more potential than CO2. And then the methane can bring gigatons of carbon into the atmosphere. So even if the amount of methane from gas hydrate melting that reach the atmosphere is not huge, but it reached the atmosphere. So it should have a big impact. And yeah, I know there are some papers by colleagues published on the source of methane, which is measured in the high scores. And most of this methane is from wetlands, for example. But as I said, most of the methane from gas hydrate melting is consumed in this process, but a small amount reach the atmosphere. But something that I have to say is that so far, there aren't any measurement done on methane emissions from gas hydrate melting. And this is something that we will do at the Center of Excellence, because in the next few years, we are working to measure how much gas hydrate there is in the marine sediments in the Arctic, and how much of this methane goes to the ocean floor and then to the column water and to the atmosphere. This is something that we will do because we are going to have a research vessel campaign together with the airplane campaign. So we are going to do the measurement from the source, so from the source beneath, the sediment beneath, and then we are going to measure the methane emissions from the seafloor through the water column and then into the atmosphere. And then this will be the first time that a group of people will do this kind of measurement. Yeah.
Thank you. Are there any other questions? I think there was one from Twitter.
Okay, the first question was from Twitter. It's from Mikel Samados, and it is, can you quantify the role of model response, internal variability, and scenario uncertainties in limiting sea ice forecast skill? It's not directed to anyone specifically.
I think I can start addressing that. And I should point out, I'm not a modeler. I'm somebody interested in observations. But one of the challenges, of course, is sea ice prediction on seasonal to interannual decadal scale. Jean-Claude showed and discussed some examples of decadal scale prediction, but of course from the perspective of human activities, oftentimes it's more the seasonal and annual that is quite important. I'm part of a sea ice prediction network, or SIPN, S-I-P-N. If you search for that on the web, you find additional resources there. That's a group that was specifically set up to get at some of these questions that that you asked about as well, and that is, what is the role of internal variability? One of the things that we're seeing is that as much of the multi-year ice, the thick volume, vanishes from the Arctic Ocean, the seasonal ice cover becomes more variable. There's more interannual variability, and that is actually quite difficult to quantify. Yesterday, we had an interesting presentation by Edward Blanchard Wigglesworth, who's with the University of Washington, who has used, along with colleagues as part of the Sea Ice Prediction Network, a range of different climate models to ask how well these climate models can represent that type of interannual variability. And I think that the verdict is still out on how well they actually help on these short timescales. So that raises an important question, and that may be what the question was alluding to, and that's the question of scenarios. What other ways do we have to help us constrain our projections of a changing sea ice cover, both on timescales of decades, years, and potentially even seasons? And of course, that's where some of the paleo data comes in. So we're looking at potential paleo analogs. The Holocene climate optimum is an interesting example where we may ask ourselves, do some of those changes we've seen then, which are well established in the paleo record, actually have something to tell us about what we're seeing now? Other approaches are simple, but simple in sort of mathematical terms, complex system models that can help us evaluate the specific types of changes that we can expect. There's been interesting presentations here at the meeting as well. Ian Eisenman, John Wetlaufer, and others have looked at this in great detail, and I think we can learn something from that. So the idea is, and again, this is part of the Sea Ice Prediction Network, is to put these different pieces of evidence in context and use, what sometimes in scientific jargon is referred to as heuristic approaches, right? You sort of, just as a weather forecaster would do. Weather forecaster sits in her office, she might look at a bunch of different model outputs, and it's still personal judgment, expert knowledge that helps build the best plausible future, a range of plausible futures out of these types of predictions. That is one of the most interesting and certainly for me personally exciting aspects of CS research these days, is that we don't understand the system well enough to be able to answer these questions that have been posed, so we have to draw on a range of different resources to try and make that fit.
Okay, the last question from Twitter is from Tom Nelson, and it's a general question to the panel. What caused dramatic 1940s to 1970s Arctic cooling? He's included a graph from Polyakov, a paper by Polyakov et al. Shows a big oscillation.
Again, can you specify? He mentioned the 40s and the 70s. I'm not sure.
Yeah, you can maybe see the picture.
What caused dramatic 40s to 70s Arctic cooling?
Well, I guess I can take a stab at that. And again, I want to emphasize that there's a range of underlying causes. I mean, if you look at climate variability in the Arctic is a comparatively small region. It has a disproportionate impact on global climate because small changes in surface albedo in the Arctic through feedback effects can impact larger areas on the globe. And that, of course, works both ways. So my understanding is that in the past, both during episodes in the 20th century, as well as going back to the 19th, 18th century, the Arctic surface air temperatures, and for that matter, for example, the state of the sea ice and other parts of the cryosphere, respond very sensitively to changes in solar forcing. And so if you have volcanic eruptions, if you have production of aerosols, and of course, in the 20th century, a significant part of those aerosols are being produced by burning of fossil fuels. Present day, sources include other types of both natural and man-made sources. So those play a very important role in surface temperatures on those timescales. Now, at the same time, and that's maybe something that Jean-Claude can speak to more appropriately, there is internal variability in the climate system. We see because, for example, the sea ice cover responds relatively rapidly, but relatively rapidly still means changes, such as what we're seeing unfold now, which is very rapid from the perspective of sea ice change. That's still changes on the order of years to decades. Once you look at ice sheets, or even mountain glaciers, ice caps, those, typical timescales are on the order of decades to centuries. And so the coupling between these different systems can cause significant internal variability.
Yeah, I can add some comments on this internal variability, which is really the nightmare for modelers. It's really the hard part. We have to really consider that the system is complex. It's the atmosphere, the sea ice, and the ocean. They all have different time response, different behavior, and in addition to the solar radiation that has a direct impact on in particular with the sea ice albedo, and which is very high. Like, I have a white shirt because all the light is reflected by this shirt, and compared to the black jackets, which is absorbing all the light. The sea ice and the oceans behave the same. So at the moment, we have this a very drastic evolution in sea ice, very drastic. Very chaotic behavior of the atmosphere, which is not at all well documented, because surprisingly we are not missing completely the weather stations for observing the state of the atmosphere in the Arctic. We only have 4 super sites for observations of the atmosphere around the Arctic, and that's it. I mean, there is nothing in the center. So the atmosphere is really a problem to address. And we have the ocean, which is pretty stable in comparison with the sea ice and the atmosphere, but we can still see some variability, and also we know that the ocean has tremendous power in bringing heat and salt in the Arctic and having a very strong influence on the system. So the combination of all these is, as I said, a nightmare for the modelers, because they have to be very good on all the feedbacks between all these elements. I just want to take an example. I mentioned 2007 as an extreme event for sea ice retreat. And I also mentioned 2012 as a second extreme event. The situation were completely different, or a lot different, as far as the atmosphere is concerned. In 2012, we had a big storm, like a perfect storm, invading the whole Arctic for more than a week. in early August and adding some breaking up actions on the sea ice and increasing the destruction of ice. But this argument is in a debate among the modelers because they are not all convinced from their model capacities that this was the real factor. So this is a problem. We are working on it. We need more data, more accurate data to address all these feedback issues, to understand more about this interannual variability. The trick is that we have to be good with the weather and good with the climate and how they are coupled together.
Thank you. We have time for one more short question, if anyone has one. If not, we'll finish here. Thank you very much for your excellent contributions. Thank you to all of those here and those watching remotely. The next press conference is in 15 minutes and is on the Anthropocene, Are We Living in the Age of Humans? Thank you.